We've already looked at three different historical models of the atom. First, we looked at J.J. Thomson, who, using the cathode ray tube, came up with the plum pudding model of the atom and is credited with the discovery of the electron. Next, we looked at Ernest Rutherford and his gold foil experiment, where he discovered that most of the mass of the atom is contained in a nucleus. Later, Rutherford would go on to discover the proton. And thirdly, we looked at James Chadwick and his discovery of the neutron using a sheet of beryllium and a sheet of paraffin wax. However, what we haven't looked at yet is how those electrons are behaving within the atom. For that, we want to turn to a fourth scientist and a fourth experiment. At this point, we'll turn our attention to Niels Bohr. Bohr was a Danish physicist who is credited with some of the earliest work of understanding the behavior of electrons within an atom. Just like we did in class, Bohr observed the gas discharge, or the light from gas discharge, coming out of a variety of different elements. He actually worked with hydrogen, as it was the simplest element with just one electron. So as you can see in the diagram here, Bohr ran a current of electricity through some hydrogen gas, and then the light that was emitted was sent through two slits and then through a prism, which split the light into its component parts. Bohr observed that hydrogen gas emitted light at a purple, a blue-violet, a blue-green, and a red wavelength. Now, remember that wavelengths of light are related to the energy that that light possesses. This is an important relationship that we'll look at qualitatively now and then quantitatively in a little bit. But again, it's important to remember that different wavelengths of light have different frequencies and therefore different energies. And maybe it's valuable to look at those three variables off to the side. We can talk about energy, frequency, and wavelength. Bohr observed some wavelengths. Those corresponded to frequencies, and those corresponded to energies. This led Bohr to a development of what was called a quantum view of the atom. His interpretation of this emission spectra was that an electron exists in a ground state, or the lowest energy state available for that electron. When a photon comes in, that's a little bit of light energy, or in the case of his experiment, some electrical energy, that electron can absorb the photon and get excited to an excited state. However, very quickly, the electron decays back down from the excited state to the ground state, and as it decays, it emits a photon of light. So again, an atom can absorb a photon of light. The electron can be excited to an excited state, but then it quickly decays back down to the ground state. We'll come back and talk about how fireworks work here. This led Bohr to an understanding of the atom in terms of a staircase rather than a ramp. Prior to his work, scientists believed electrons could exist at any energy level, sort of as if an electron could exist anywhere on this ramp. However, remember that spectra that Bohr observed? He only saw 4 different shades of color, or 4 different wavelengths of light, right here. In fact, there's 5 in the drawing, but still, he only saw discrete wavelengths of light. What that led him to understand was that the electron really couldn't exist anywhere in relation to the nucleus of the atom, but it had to exist in discrete steps, either on that step, or on that step, or on that step. This led to a staircase view of the energy of an electron. The reason Bohr was able to deduce this is that the electron gave off, again, those finite wavelengths of light, which relate to finite amounts of energy, which in turn relate to finite changes in energy for the electron. An electron cannot move from any arbitrary position along this ramp to any other arbitrary position, but it must move from one step to another step. In the diagram here, we can envision the bottom step, or the ground floor, to be a ground state, and any of those higher steps being excited states. Regardless of which step the electron winds up on, it has to wind up on a step and not in between. By restricting the position of the electron to distinct steps, you restrict the changes in energy of the electron to distinct amounts, which then lead to specific wavelengths of light or colors of light being emitted. Here's a diagram that summarizes that explanation. There's kind of a lot going on here, but we can look at the diagram on the right specifically and look at the nucleus of an atom in the center and then the different levels that an electron is allowed to exist at, labeled here as N1, N2, N3, etc. And notice how if the electron moves from N equals 3 down to N equals 2, it emits red light. If it moves from N equals 4 to N equals 2, it'll emit blue light. What you don't see is you don't see an electron moving from between two different energy levels. And again, Bohr realized that had to be the case because he didn't see every change in energy possible. He only saw specific changes. This gives us two important physical attributes of an atom. One, electrons need to exist in specific energy levels or specific quantum energy states. And two, atoms can only absorb certain amounts of energy because they can only promote the electron to certain levels. A hydrogen atom will only absorb certain wavelengths of light because it can't move an electron to any arbitrary energy level. This brings us lastly to fireworks. The brilliant colors you see when fireworks are emitted is due to the changes in energy levels of electrons in those atoms, in those elements that are contained within the fireworks. The purple light corresponds to a very specific energy change in whatever element that is. The red light to a specific energy change in that element. The yellow light, specific energy change in that level. This understanding, this quantum view of an atom, is a little bit of an oversimplification, where the model works with hydrogen and just one electron, but breaks down a little bit when you deal with more than one electron. We're going to need to modify this ring or this orbit view of an electron, and based on the work of these two scientists, Erwin Schrodinger and Louis de Broglie, translate this orbit view into a more complex 3D orbital view. In our understanding of the atom, we've progressed from a hard, unbreakable sphere of John Dalton to the plum pudding model of J.J. Thomson, to then a small nucleus model of Ernest Rutherford, most recently to this quantum view of Niels Bohr, and then what we'll look forward to is the orbital model of Erwin Schrodinger and Louis de Broglie.